Argo Space, a US-based startup, plans to harvest lunar ice and transform it into water to power a transportation service, delivering cargo across low Earth orbit and cis-lunar space. Realizing this vision will take time, the company's near-term focus is deploying space tugs to reposition small satellites into custom orbits after their launch into low Earth orbit. Argo Space, founded by three brothers who previously worked at SpaceX, has created a system to harvest lunar regolith, the rocks, dust and debris blanketing the moon's surface, as a key part of their long-term vision. In addition to the water harvesting business idea, they have a broader vision that includes water-fueled orbital transfer vehicles, essentially space tugs, and orbiting propellant depots. Together, these elements form a comprehensive cis-lunar transport system powered by water. To grasp their business model, picture this analogy. Rockets are like cargo ships docking at a port. Once the cargo arrives, it's loaded onto a lorry, or truck as Americans say, to reach its final stop. Argo is building the space equivalent of lorries. These space tugs pick up cargo in low Earth orbit, move it to their final destination, and return to LEO to refuel for the next trip. Is water the most efficient fuel for a space tug though? No. But it is cheap, safe and readily available on the moon and throughout the solar system, provided you've mastered the tech to prospect, mine and extract it. Argo isn't the only company thinking along these lines. Interloon and Ethos, two companies I've reported on previously, both have lunar mining plans. However, Argo stands out as the only company primarily focusing on water. Carmen Plus, a company I've also recently reported on, has plans to mine near-Earth asteroids for water, using a water-fueled space tug to ferry the water back to LEO to fill orbiting propellant depots. And I've reported on space startups working on providing orbiting fuel depots, such as Spacium, who could be a potential customer for lunar or asteroid water. We'll examine the practicality of mining and extracting water ice and using it to fuel space tugs and satellites in low Earth orbit. But first, let's take a look at the water-fueled spacecraft. Argo's space tug, the Argonaut. Argo is developing a large, reusable and refuelable space tug dubbed the Argonaut, capable of ferrying payloads of up to 1,000 kilos, that's roughly 2,200 pounds, thanks to its high-impulse plasma thruster. More on those engines later. Looking ahead, future iterations will handle heavier payloads, as much as 10,000 kilos or 22,000 pounds. These vehicles support on-orbit pickup of cargo and are built to withstand at least 10 transport missions. What powers them? Water. Here's how it works. A customer launches their payload on any rocket. An Argonaut already orbiting picks up the cargo and delivers it to its final destination. Alternatively, the tug can launch with the customer's payload already attached. Once the job's done, the Argonaut swings back to refuel, ready for its next assignment. Technology. Argo Space has not disclosed the exact details of how they power their space tugs, other than it's propelled by water. The company did clarify their space tugs use water plasma thrusters. This is not entirely new technology. In 2021, NASA launched a payload to demonstrate water-based propulsion in space. A water plasma thruster works by ionizing the water into a plasma using electric fields or microwaves, then ejects the plasma out of the end of the spacecraft by using electromagnetic forces. The charged particles in the plasma are expelled at extremely high velocities, generating thrust. ISP, a measure of thrust efficiency, can reach 1,000 to 5,000 seconds, far in excess of chemical propulsion, which tops out at about 450 seconds. The downside is thrust is much slower than chemical thrusters, so it's good for slow and efficient movement of cargo, but not suitable for quick deployment of payloads. Another option would be to split water into hydrogen and oxygen via electrolysis, then combine them in an explosive chemical reaction to generate thrust. This packs a bigger punch, but sacrifices efficiency. Looking at this post from Argo, we now see that their propulsion system is dual mode. Water used as a fuel is flexible. It can be used as a source of plasma for high efficiency but slow transport, or be broken down into hydrogen and oxygen for high thrust, less efficient burst. As they put it, water is the oil of space, a resource that can power the off-world economy. Why use water for powering a space tug or satellite? Why has Argo Space chosen water as a propellant for their space tugs? Well, let's go over some of the advantages of using water to propel spacecraft. Water is cheap and abundant. Water is low cost, at least on Earth. That's because it's readily available and doesn't require much in the way of processing, handling, or storage. Water simplifies logistics and operations. The Carlyle brothers, former SpaceX staffers, know firsthand the headaches of managing cryogenic fuels. On Falcon 9 rockets, those ultra-cold temperatures can wreak havoc on seals, valves and other bits. Water, by contrast, is a breeze to handle. It's non-corrosive and can sit in storage for ages, making it perfect for in-space fuel depots or long-haul missions. Water is safe to handle. Many current space propellants are toxic, demanding careful handling to avoid contamination. That ramps up costs and complicates operations. For example, a return payload, like a life science experiment, can't be handed back to customers straight away. First, the vehicle needs decontaminating, and any lingering toxic fumes must clear. If you've ever seen a Crew Dragon capsule return, you'll notice divers sniffing around with sensors to ensure it's safe before popping the hatch. Water sidesteps all that drama. Water is everywhere. Water seems to pop up wherever you look in the solar system. Suspected oceans lurk beneath Europa's surface, asteroids drifting near Earth, and Mars boasts hefty reserves on its surface. It's practically ubiquitous. Once we nail the tech to prospect, mine and extract it, water can fuel travel across the solar system, while also serving up drinking water, life support, plant irrigation, showers and more. Mastering water-based tech could unlock free, boundless movement throughout the solar system. Tapping into water reserves opens fresh business prospects in space and paves the way for a lasting human presence off-world. To be fair, it's not all upside with water. There are some problems. Let's address them now. Challenges with water. In a nutshell, water freezes in space. So you have to engineer solutions to keep water in a usable form, and that adds complexity, cost and challenges. In reality, you just need to insulate the water propellant tanks with some modest heating and you're good. Spacecraft already use heaters for instruments and fuel lines, so no new tech is needed for water propellant. It's much easier than handling cryogenic fuels. Another problem is a water plasma thruster has low thrust, the same as all other plasma thrusters. Argo sidesteps this with their dual mode engines, a high thrust chemical reaction mode or a high efficiency plasma mode, depending on the job. Both modes used by Argo consume a large amount of energy. For the chemical side, water must first be split into hydrogen and oxygen via electrolysis. The plasma thruster, meanwhile, requires high-powered electromagnetic fields to ionize the water. This means more solar panels and batteries beyond what non-water spacecraft need. This adds additional weight and complexity. Water purity may be another issue. When you're sourcing your water from the moon, it comes laced with all kinds of contaminants, such as dust, minerals or volatiles. For plasma thrusters, these impurities might clog or corrode the ionization kit. On the chemical side, they could muck up reactions or chew through electrodes. Water availability is a problem. Lofting water out of Earth's deep gravity well is pricey, but harvesting it from the moon or far-flung asteroids is not easy either, at least not yet. None of these issues are deal breakers, but whether Argo could chart a clear course to profit remains up in the air. Where is the best place to mine water? Argo wants to harvest water from the moon, but is that the best place to source water from? Let's consider the options. Earth. Earth has plenty of water. Unfortunately, it's at the bottom of a very steep gravity well. Or to put that into numbers, you have to accelerate payloads to over 9 km per second to move water into LEO. Here is a simple graphic to visualize gravity wells of potential sources of water. The number underneath is the escape velocity, the velocity needed to escape from the gravity well. Now, depending on where your fuel depot is, you may not need to escape entirely. For instance, for an orbiting fuel depot in LEO at 400 km, you need a delta V of about 9.6 km per second, still extremely expensive from an energy point of view. What's clear from the graphic is that, from an energy point of view, The Earth is the worst possible place to source water from. Where else then? Well, there's the Moon. It's estimated the Moon contains 6.8 billion tons of water. Water ice can be found near the South Pole and in permanently shadowed craters. The Moon is a huge improvement. Even better if you have an orbiting fuel depot in low lunar orbit. The delta V is just 1.9 kilometers per second. That's the standard figure used in lunar mission planning. Mining water on the Moon has problems, including uncertainty about the yields, which is based on the chemical composition of deposits. It's likely the water ice could be laced with contaminants that will have to be removed. Additionally, lunar dust, sharp, fine and electrostatic, tends to cling to surfaces and infiltrate machinery and excavation equipment, posing further difficulties. NEOs have hardly any gravity, so escaping from them is trivial. For instance, from a 1 kilometer NEO, you can reach escape velocity using a fire extinguisher. This means the delta V to rendezvous with them, extract water and return to low Earth orbit could be the most cost-efficient method. Plus, as we've seen, their gravity is so minimal that escaping it poses little challenge. The downside is you have to operate in deep space, which in practical terms means you are mining and extracting autonomously using robots, no humans in the loop. So if something breaks, that's the end of your mission. Unlike the Moon, where an astronaut with a spanner may be able to fix the problem. Let's go over some of the key milestones for Argo Space so far. In November 2023, Argo partners with Astrolab to deploy water extraction technology on the Moon. Astrolab has signed a contract with SpaceX for a mission to the Moon using the Starship vehicle. It's scheduled to launch in 2026 and Argo Space has a payload on board. Once landed, Argo will deploy a demo of the technology to harvest water from the lunar rocks and debris. If you are not familiar with the Astrolab lunar rover, check out my in-depth video on them. Argo Space has raised a total of $12 million in various funding raising rounds and received about $2 million from the US Space Force for work on in-space transportation. Crosslink, one of the investors in Argo Space, had this to say about the company. We are excited about their vision to transform space transport and mobility systems. The space transport and mobility systems Argo are creating have clear near-term utility across commercial and defense use cases. The team's vision for a multimodal logistics architecture using in-space refueling and propellant sourcing will open up access across all orbits and enable unconstrained, dynamic operations in space. What Argo is building has the potential to fundamentally change how we build space systems and how we operate in orbit." Unquote. Argo is using the investor funding to develop and build the first Argo space vehicle that is expected to launch in the final quarter of 2025. In addition, the funding will help them hire more employees to accelerate their growth and fund a new headquarters in California. This new location will house design, manufacturing, build, and test the Argo space transport vehicles and the lunar surface hardware. Upcoming events. In a few days, Intuitive Machines will land a lunar rover on the south pole of the Moon with a payload that will drill up to 1 meter below the surface to look for lunar ice. Another payload has a mass spectrometer to identify the chemical composition of the extracted material. The iSpace mission, currently in deep space, is expected to land on the Moon in June 2025. The company's vision is resource extraction on the Moon. A rover on the lander is designed to explore and collect lunar rocks as a first step towards mining and extracting resources from the Moon's surface. Another payload will attempt to extract water from the lunar surface by heating rocks and capturing steam, then electrolyzing the steam into hydrogen and oxygen for storage. Exciting times ahead for commercial lunar operations. What do you think about using water to fuel space tugs and satellites in low Earth orbit? Could water ice be the resource that powers our expansion off-world? Leave your comments below. Okay, that's it for this video. Thanks for watching. Be sure to like and subscribe so you see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.